Now?
Okay. All right, welcome. It's our Tuesday edition of physics class. Up here, I'm starting a little list like I normally do of the formulas that we are needing for the mod. So, yesterday I forgot to videotape this, so everything that you'll need from yesterday we'll go over right now in the quick and condensed version. All right, so what two things multiply together to give us momentum? Is that still in your mind, MM?
Mass and velocity.
All right, mass and velocity. What unit do we use for momentum? Alex, what unit do we flush out when we're talking about a mass times a velocity?
We do use seconds.
Mass, yeah, seconds is in there.
Yeah.
Mass is what?
Kilograms.
And then velocity.
Is meters per second.
Alright, so putting it together, we get kilogram meters per second, which we chose not to rename. So, then we established another formula by all coming to the board, and the end result was what, MK?
Force times change in time.
Alright.
And that has a name. We actually named that. Do you have an impulse to answer that question, MD?
It's impulse.
Impulse, alright. She's an impulsive person. That's called impulse. And other years, we've called that the fat equation because it looks like the word FAT. So that's another way we can call it. It's really not an A, it's a triangle. But it looks like it from a distance.
Nowadays.
So it's been named by some other classes, the fat equation. Alright, and then we discussed how, if we are using an airbag, how this impulse or fat equation helps us. So when we did that, we discussed that in a traffic accident, the mass that the car you're in and the car that's hitting you, or the pole or whatever's hitting you, is set, and the velocity is set. So this is going to be a constant. Unfortunately, we can't mess with that. That's been determined. So, however, we can mess with this over here. So, which one do we want to be lower? When you're in an accident, you don't want the force to be high, you want it to be low. So to keep this constant, if this number goes lower, what happens to this number, Alex?
It has to go up.
Right, so that's what the airbag does for us. It increases change in time, so F goes down. And what way, can you explain, MK, why? How does an airbag increase the change in time? Was that made clear to you yesterday? Right, the time of contact is increased, but how does that happen with an airbag? Why not just use the dashboard to increase the time? Because the material itself is softer, it's not because it's soft you're going to have less force. It's because it's soft that your time of contact, you're going to smush into it a little bit. And anyone had an airbag experience? Did your airbag go out?
No, I didn't.
It did.
No.
Wow.
Because we were only like 25.
Okay, I've never had an airbag experience, thank the Lord. But anyway, apparently it's going to be softer than the steering wheel or the dashboard, the windshield, or pole, so you're going to sink into it. That's not why. I do not say that's why that it will decrease the impact of the accident. It decreases the impact of the accident because that cushion increases the time of contact with your head, so force has to go down to keep this a constant. Alright, so that's where we ended yesterday. Look at your notes, was there any major point I forgot about? Because again, I'm recapping for your yesterday's absentee students.
It would be the vector and scalar.
Oh yeah, that's true. So so help me with that, MD. Is momentum a vector or a scalar?
It's a scalar.
Momentum.
I think so. It's a vector.
Alright, it's a vector. Because it is a mass, which is a scalar, times a vector, that means it must be a vector. So that's all I'm going to say about that right now for them. Alright, so that's the main points from yesterday. Any questions about that? Alright. We started yesterday with this kind of problem, and we had a 345 kilogram car traveling at that velocity. So just putting the mass and velocity together to get momentum. Can you peek at your work and tell me what came out, Alex?
6,590 kilogram meters square per seconds.
Yeah, kilogram meters per second, right? So, viewers from home, we did this problem yesterday, and that was the answer. So that brings us up to where we are practicing with the impulse equation. So, if you would, we started this with a little demo yesterday. And so we're going to draw the problem. We have a golf club and a ball, not drawn to scale on my board here. Golf balls aren't that big relative to the clubs. So if you would draw a golf club and a ball, indicate that the ball is coming off of the club at 30 meters per second. That's a 30.0. So we have 3 sig figs going there. And the golf ball is 0.100 kilograms, and it's coming off at a 45-degree angle. And the time of contact between the golf ball and the golf club is 12 seconds. That's a lot. 0.12 seconds. Find the force. So draw that out, and then we're going to work it together. You're in impulse training. I'll give you a second to draw the problem out and put down the numbers. I wanted to try this too. It looks so easy on TV, you know? Pretty good.
That was a good swing.
Good backswing and everything.
If you get the form right, then you'll get the,
Where did it go?
I
I know people don't do golf. So
I don't
zing through the wall.
I do
there.
golf sometimes.
You may go
That's
okay.
just on occasions.
Alright,
Oh
we'll
my
see you
God.
later if anybody else wants to try it. Alright. Got it down? You got the picture down? Alright, pull out. You want to pull out when you see that we're looking for force and it involves time, you're going to pull out the impulse equation. So, change in momentum equals fact. F, change in t. When we do that, we are going to put in some values, so I can see right away that my time, the change in time, is going to be 0.12. I'm looking for force, so that will be in my equation. I'll solve for it in a minute. But what am I going to put over here for change in momentum? We kind of have to work backwards from what we saw yesterday, when a way that we can write change in momentum is whenever there's a change, there's 2 quantities, a first and a second, and the change is in between. So I'm going to get rid of the change symbol and put momentum final minus momentum initial. So that is what the change is. And then I'm going to go backwards again. You saw some of this going in the other direction yesterday. I'm going to change momentum final to mass velocity final and mass velocity initial equals F.12. Now I should know everything. So, if you would then, MK. Let's say we have M, this mass and velocity or go together. For final, let me rewrite this up a little higher. Alright, so MK, start putting in some numbers for me.
So mass 0.100.
0.1. I'll just use the 0.1. So for space, do we have a velocity final? What is it?
30.
Right. So after this ball
Keep
has
it right.
been struck, hit by the club, it should be traveling in its final velocity. All right, what about initially, before it struck? MK as well.
Mass is the same, velocity 0.
Yes, it is. Do you see that? Initially the ball is still, so that term will actually zero out and will not bother us. All right, so go ahead, and if you have the luxury of a calculator that works, please tap out force for me. And we've got, I don't know how, I've never known exactly how to count angles with sig figs.
Same.
I've looked it up so many times, and it's so confusing that I've never been able to teach it well. Actually, I know a physicist. I'm going to ask her, see what she says. Can you dummy it down for me? All right. So what comes out? Let's just say, let's say 3 sig
25?
figs.
And this one I got.
What'd you get, Alex?
I got 25.
All right, 25. So is there another decimal, or is it just?
It's just 25.
All right. So I'll say 25.
5.0.
Because it's the 2 sig figs is 0.12, right?
Oh yeah, you're right. I keep forgetting these things. All right, so we're stuck with 2. 25, and what unit is force in, Alex?
Force is in Newton.
Right, got that one down. Very good. All right. All right, so that's how you use the impulse equation. The tricky part is knowing what to do with this change. So you have to get that into 2 quantities. All right, try this one. It's like it. I'll remove this one. I wonder how long I've talked. Let me set up this equation and then we'll shut it down. I've set up this problem and then we'll shut it down. All right, so this time draw a baseball mitt. Did you bring one, Alex?
I couldn't find mine. I actually
Oh my
like.
goodness.
I don't know. Like all my baseball stuff was like gone. Like I don't know where it's at.
How's that?
Cause like I used to play a lot in spring like with my friends, and then like, since the spring it's like not there anymore. I'm like
All
maybe my
right.
mother hit it or something.
The ball is coming toward the glove. The glove is actually going to, as we learned earlier, action-reaction. The ball will have a force on the glove will have a force on the ball. The one I'm going to give you is the force of the glove on the ball, and that's going to be 55 newtons. And the ball has a mass, 250 grams. And the velocity of the ball as it enters the glove is 22.1 meters per second. And this time I want to find how long it takes to stop the ball. Obviously it's going to come to a stop, but I want the time of contact before it's actually stopped. Find how long to stop the ball. So that's the change in t. Alright, we're going to work that problem out and come back on the next part of the video and show you the answer. So we're going to say over and out for now.